All right, so like I said, I get this zoomed out just a touch. We're going to cover sections 5.3, 5.4, and 5.5. So 5.3 actually starts with sorry. Okay. I have to jump on real quick. Get my attendance all caught up. All right, so like I said, 5.3 actually starts with some terminology that you need to be aware of. So they're going to ask you some questions about this. So first things first is a term. A term is simply a number or the product of some number and a variable or more than one variable to some power. Okay, so it could be just a number or just a variable, because that would be 1 times that variable. Or you could have some product of lots of variables. Or you could have some product of variables to various powers. All of those are examples of what we call a term. And then if you have multiple terms, that makes up what is called a polynomial. So a polynomial has multiple terms combined by addition or subtraction. Subtraction is just adding the opposite. So a singular term like these are actually could be referred to as a monomial. So a monomial is 1 term. So then a polynomial is multiple terms, like x plus 5 or x squared minus 3x minus 2 or x cubed y plus 4ab minus 12, something like that. Specifically, anything that has 2 terms is referred to as a binomial. Anything with 3 terms is referred to as a trinomial. So like that, again, I'm talking about the whole thing. And then if you have more than 3 terms, so if I threw another, let's just add a number on here. So let's add a variable, so barely see that, say that's a P. Anyway, so say we have 1, 2, 3, 4 terms. It's just referred to as a polynomial. So anything more than 3 terms, okay, it's just called a polynomial. So if you had 5 terms or 6 or 7 or 8 or whatever, okay, then it's just a polynomial. Okay, but all of these are polynomials. Just specifically, if there are 2 terms, it's called a binomial. 3 terms is called a trinomial. Anything more than that, you just call it a polynomial. So the first couple of problems in this homework ask you some specific definition stuff, like how would you classify this polynomial? Okay, it's a trinomial, yada, yada, yada. So just understand that. And the terms are separated by either addition or subtraction, because subtraction is still technically just adding the opposite. So like minus 3x is the same as saying plus negative 3x, or minus 2 is saying the same plus negative 2. So it's combined by addition. So the addition is what separates a term. So it's not about the number of variables you have. Like these are all 1 term because there's no addition in here. The addition is what separates your term. So this is a term of x and a term of 5. So if you have 2 terms, that's a binomial. This is a term of x squared, a term of negative 3x, a term of negative 2. So this makes it a trinomial. Okay, now each term can also have a degree. So the degree of a term is the sum of the exponents of the variables. So if we do that same list of terms, so 5 for x, or 3xyz, or 3xy squared z to the third, okay, that same list we had up here at the top, we can find the degree of each of these. Now, it's just the sum, which means to add the exponents of the variable. So if there's no variable, then there's no degree, okay? If you don't see a variable, then the degree is 0. Also, remember, if you have a variable but you don't see the exponent, remember that exponent's automatically a 1. Do this in a different color so it stands out a little bit. Okay, remember, if you don't see the exponent, it's a 1. So this x has a degree of 1. Okay, so same thing, the 3 doesn't, we're not worried about the exponent of that, but of the variables, x and y and z, so the x has a variable of, or exponent of 1, the y has an exponent of 1, and so does the z. So if we add those together, this term has a degree of 3. And then same thing, this x has an exponent of 1. So if we add, we take the sum of the exponents, 1 plus 2 is 3, plus 3 is 6, then this term has a degree of 6. So each term will have its own degree. And just like each term can have a degree, there can also be a degree of the whole polynomial. And it is simply the highest term degree. So I'll show you a couple of examples of what they might ask you. So they'll say something like, classify the polynomial. Or how would you classify the polynomial? Or what would you call this or whatever? And they'll give you something like x squared plus 3x plus 7. Okay, so first off, we have 3 terms. So this would be a trinomial. And this particular term, the x squared, has a degree of 2. If you don't see an exponent, it's a 1 there. So this x, 3 times x, has a degree of 1. And then this 7 doesn't have a variable, so it has a degree of 0. So the degree of the whole polynomial is simply the biggest one. So the biggest is the degree of the whole polynomial. So then we would say this is a trinomial with a degree of 2. Okay, they told us to classify this one. So we've got x, y to the second, minus 4, a to the third, b to the fourth. If we have two terms, that is a binomial. We add the powers of the exponents. This first term has a degree of 3. This one has a degree of 7. So the biggest one is the degree. So this would be a polynomial with a degree of 7. Okay, so each number or product of number and variables is a term. When you have multiple terms, that's a polynomial. 3 terms is a trinomial, 2 is a binomial, anything else is just classified as a polynomial. So 4 terms, 5 terms, 6 terms, whatever. Each term can have a degree. It's the sum of the exponents of the variables. And then the whole polynomial can also have a degree, and it's the biggest term degree. So when you have multiple terms, you got to find the degree of each. The biggest one is the degree of the whole polynomial. So same thing, multiple terms. This one's degree 3, this one's degree 7. So the whole polynomial has a degree of 7. So like the first 3 or 4 questions on your homework are going to be along the lines of how would you classify this polynomial, or what would you call this? Okay. And again, remember each individual term, if it's just one of these guys, that's called a monomial. It's not a polynomial till you have more than one. Okay. So that's just kind of like some housekeeping stuff that they may ask you right off the jump. Then what we're going to do with it, primarily the focus of section 5.3 is adding or subtracting polynomials. And this can be summed up pretty conveniently in that you can only, or how to spell, add like terms. Okay, remember that. That's extremely important. Okay, the only thing you can ever add in math are your like terms. That's how we were able to solve equations. We could add our x's together, or we could add our regular numbers together. You can add x squareds together. Like terms have the same variables to the same exponents. For example, if I told you to add 3x plus 7 plus 4x minus 5 minus 2x minus 3x plus 1, or something ridiculous like that. Okay, we can combine the things that are like. So the 3x and the 4x and the negative 2x and the negative 3x. We can combine all of those. We can add those pieces together. So 3x plus 4x is 7x. 7x plus negative 2x is 5x. 5x plus negative 3 is 2x. So again, we can combine those like terms. Anything with an x to an exponent of 1, we can combine. Okay, same game. Any of the numbers with no variables, those are called constants. Okay, we can combine those. So the positive 7, the negative 5, and the positive 1. So 7 plus negative 5 is 2. 2 plus 1 is 3. So we can combine this or simplify this by combining our like terms. When you combine your like terms, you simply add or subtract the numbers in front, and you keep the variable as it is. So they're going to give you some stuff like this. okay? You got to pay really close attention because a lot of this looks like it can all go together. I just see a pile of numbers and X's and Y's. Okay, but look at each term individually. So this one has 3 X to the second and Y, where this one has 2X and Y to the second. Again, the only like terms are going to look just like this. You're going to have an X to the second power and a Y to the first. So if it helps, you might want to write those ones in. You don't have to, but you can. Okay. So this 3X to the second Y can only combine with any other X to the second and Y. So I can combine these two together. So I've got a positive 3X to the second Y and a positive 4X to the second Y. So if I can combine those, I get a 7X to the second Y. If I have 2.
So we don't add the variables together too?
Nope. When you combine like terms, it's kind of like this is telling me what it is, and this is telling me how many I have. So if I had 3X milkshakes and 4X milkshakes, I've got 7X milkshakes. Okay, whatever you want to call these things, apples, bananas, whatever. Okay, so it's like the 3 is how many I have of this thing. Does that make sense?
Yes. And what about the powers? The X squared and the X squared from the 3X to the 4X, would you not add those together?
Okay, so again, these two are the only things we're combining. We add the 3 and the 4. That's where the 7 came from. And then the X squared Y, we just kept it the same. So keep your variables and your exponents the same when you're combining. So this one, the 2xy to the second, we can add it with this guy, the negative 4xy to the second. So then we can combine these. If I had 2 of these things minus 4 of these things, then I've got negative 2xy to the second. And then last but not least, I've got a 3x. I've got another 3x, so I can combine those to get a 6x. So when you combine, you only add or subtract the numbers in front. You leave the variables alone. And I can't combine these because they're not the same. This one has an X to the second power. This one has a Y to the second power. These two are different, so I can't combine them. They look really close, but they're actually different. So that is as simplified as that gets. So to be a like term, they have to have the same variable to the same power. So even though these both have X's and Y's, this one, the X is being squared. This one, the Y is being squared. So again, that makes them different. You can't combine them. Okay, subtraction. Okay, we talked about this. Remember, subtraction is the exact same thing as adding the opposite. So minus 5 can become plus a negative 5, just like minus 2x can become plus a negative 2x. That's how we do subtraction with polynomials. So if I'm subtracting this whole thing, okay, it's kind of like distributing a negative 1 to everything inside. So we get 5a plus 6 plus negative 3a and then positive 7. So negative 1 times 3a becomes a negative 3a. Negative 1 times negative 7 becomes a positive 7. So when you subtract a quantity, you have to distribute that subtraction. So then when we combine our like terms, 5a plus negative 3a would give us 2a. And then 6 plus 7 would be 13. And again, we can't combine the 2a and the 13 because those are different. And that's really kind of the rest of what they're going to do. They can make these more complicated and they can give you more terms to have to combine. But really, this is about as ugly as a problem would get. When you have a lot of the same kind of variables, just slightly different, you just got to really pay attention to if they're exactly the same thing, like the x squared y's or xy squareds. Most of the problems, they choose completely different variables or don't have a variable at all, so it's not nearly as confusing to combine them. Along the same game, you got to distribute your negative. So that becomes a negative y, and then that would become a positive 2. Combine any like terms, we have a positive 4x squared and a negative 2x squared. We have a positive 3, we have a positive 2, and another positive 3. That would be a positive 8. Also remember, if you don't see a number in front of a variable, it's automatically a 1. So that's a negative 1y. You don't have to put that there, but you can. In fact, I don't think my math lab likes it there. I actually do like it there. I would rather put it there, but it's not necessary. But that's what that one would look like. So 5.3 is going to start out with some kind of definition stuff and ask you to classify some of the polynomials. And then the bulk of the assignment is going to be a bunch of this adding and subtracting of polynomials. And the only other goofy thing they might do is they might take a function notation like this. And they'll give you another one, say r of x is x squared minus 1. And they might tell you to take the f of x plus the r of x, which isn't anything fancy. It basically just means take f of x, which is this thing, plus r of x, which is this thing. So it's still just adding them together. It's just giving you a different look. So it's telling you to add 3x squared plus 2x plus 4 plus x squared minus 1. So it's literally asking you to do the same thing. It's just making it look a little different. So again, combine like terms, 3x squared plus 1x squared is 4x squared. This 2x doesn't have a like term, so we just keep him. And then positive 4 and negative 1 is a positive 3. I think we talked about this, but I can't remember if it was in a different section or not. This f of x is just a function notation. We did talk about whether or not something was a function. Okay, but anyway, this f of x, like this. So if they tell you to evaluate, say, the f of 2, all they want you to do is plug that 2 into the f function, 4x. So that 3x squared means 3 times 2 squared. So if they replace x with 2, they want you to do that. They want you to put 2 in place of the x. So then 2 times 2 and then plus 4. So if this is your f of x function, if they want the f of 2 or the f of some number, you're just plugging that number in for your x. And you can just follow order of operations. 2 squared is 4, 2 times 2 is 4. 3 times 4 is 12. 12 plus 4 is 16 plus 4 is 20.
I have a quick question on that.
Yep.
Now the function of x, if there's another variable, like say there's like 3x squared plus 2y,
Yep.
now that will only go into the x's, right? It doesn't
Correct.
go into the y's?
Does not go into the y's. It only goes into the x's. So if this is a function of x and they tell you to replace the x with 2, that would be it. So my 4 kind of looks like a y. So we would not replace that y. It would stay whatever the heck it was. So if for some silly reason this was a y, okay, then this would have stayed a y and we would not have been able to combine it. So we would have 16 plus y in that case. So yeah, it only replaces the x. Okay, and they can do a couple of different things. So if we did one for the r of x function, so if they told me to take the r of -3, get where I can see everything on there. So the r function is x squared minus 1. So the r of -3, they want me to plug in -3 for the x within the r function. So x squared, so I'm plugging -3 in. So remember, -3 in parentheses squared is 9. 9 minus 1 is 8. So I think they might ask you to evaluate like one of the functions or something like that. So if they just want you to do that, just plug the number in. They're not asking for anything crazy. Most of what they want, because again, that follows with what this section is all about, is they're going to have you add the two functions together or subtract them or whatever. Okay, so that's adding polynomials. 5, 4 is multiplying polynomials. Adding is easy, multiplying is easy. The problem is people confuse them, okay? They look similar, but they behave differently, okay? For example, if I told you to add, so this is adding. If I told you to add 3x plus 2 plus 3x minus 2, we can just combine like terms. So we combine our 3x and our 3x to get a 6x. We combine our 2 and our -2 to get 0. So we could write 6x plus 0. That'd be kind of silly, so we just leave that as 6x. Okay? However, multiplying goes back to that order or properties of exponents. Okay? When you multiply, you can only add like terms, but you can multiply anything. So if you have a quantity times a quantity, you have to distribute everything. So we've got to take 3x times 3x. Okay? And we've got to take 3x times -2. And we've got to take that 2 times 3x. And we've got to take 2 times -2. So we've got to multiply all of those kind of pieces together, see what we get, and see if we can combine anything. So anytime you have a quantity times a quantity, you got to do all this distribution. So again, adding is silly, really easy, okay? Just combine your like terms, nothing to it. Multiplying gets a little more complicated. You got to distribute from one parentheses to the other set. You got to multiply all those things together. Also, when you multiply, remember your properties are, we actually did problems like this in 5.1, okay? 3x times 3x, 3 times 3 is 9, x times x. Now we add those exponents together, and that would be an x squared. So the numbers we multiply, and then we add exponents of the same base. So 3x times 3x is 9x squared. 3x times -2 is -6x. 2 times 3x is positive 6x, and 2 times negative 2 is negative 4. We can actually add those two things together because they're the same. Positive 6x plus negative 6x is 0 x's. So when it's all said and done, we have 9x squared minus 4. So adding is not difficult. Multiplying is not really difficult, but they're very different. And the only difference is literally the symbol between them. So don't confuse which one you're doing where, okay? Adding is simply combine like terms. That's it. You don't change the variables. Multiplying is lots of distribution. Okay, and kind of the rules are you'll multiply the big numbers and you'll add the exponents together of the same base. So we'll do a few more examples of that. We'll actually start with some more simple problems, then we'll progress to some of the ugliest ones. Okay, so again, multiplying. You can only add like terms, but you can multiply anything. If we take 3x squared y times 4x y squared z cubed, okay? Again, we did problems like this in 5.1. If we would go back to our notes from 5.1, we probably did this same problem. If not, we did something very, very similar. Okay, the way we do this is we can multiply the big numbers, the coefficients, and then the shortcut is to add the exponents. And remember this x, if you don't see an exponent, it's automatically a 1. So x squared times x is x to the third. This y is y to the first, so y times y to the second is y to the third. And then the z would be z to the third. Because there's no pluses or minuses, there's no distribution here. We're just multiplying these together. This is one term and this is one term. You multiply the big numbers together, you add the exponents of the same base. I just did different colors so you can see that a little bit better, hopefully. Okay. They told us to take -3 times x squared plus 2x plus 1. Again, if you have a number or variable times some quantity where you're adding or subtracting, again, that turns this into a polynomial. Okay. Again, this is where we got to do distribution. Anytime you have a number outside times a bunch of things inside, we've got to do that distribution. So -3 times x squared is -3x squared. -3 times 2x is a -6x. And -3 times 1 is -3. And again, we can't combine any of these because they're all different. X to the second, x to the first, no x.
So if -6 was -6x to the second,
then we could have put those two pieces together.
Right, but the variable and the power would have stayed the same. It's just the base number that would have changed, correct?
Correct.
Okay.
Yeah. So like when we combined the negative 6x and the positive 6x, that became a 0x. So we added the numbers in front, but we didn't change the variable. When you have 0 of anything, there's no need to put it there. So that's why we didn't have it there. But say this would have been like a negative 2x and a 4x, then that would add together to be a 2x. So yeah, when you add, the variables don't change. You just add or subtract the numbers in front. And as you can see, the more stuff you multiply, the more distribution you have to do, and the bigger the problems get. Okay, I want to do 2 more examples from this, just to kind of get some practice with it. So if we had 3x to the 4th plus 2y times 3x minus 1, or something like that. Okay, again, multiplication. If you have a quantity times another quantity, we got to do a bunch of distribution. So we've got to multiply everything in the first set times everything in the second set. So we have 4 terms. There's going to be 4 different multiplications. So we've got to multiply 3x to the 4th times 3x. So that would be 9x to the 5th. So again, multiply the big numbers. 3 times 3 is 9. Add the exponents. If you don't see an exponent here, it's a 1. So the 4 plus 1 becomes a 9x to the 5th. 3x to the 4th times negative 1 is a negative 3x to the 4th. 2y times 3x is 6xy. Order doesn't matter. So if you did 6yx, that's perfectly fine. Typically, you'll write them in alphabetic order because x comes first. You'll put the x first, but that doesn't matter. And then 2y times negative 1 is a negative 2y. Then I would look to see if I have any like terms. I only have 1x to the 5th. I don't have any other x to the 5ths. I just have 1x to the 4th, no more of those. I have an xy and a 2y. I can't combine anything, so this is the simplified answer. All right, I'm going to do one more example. This is as ugly as it gets. So this is the worst possible problem you'll see within a unit like this. If they give you 2 terms times 3 terms, okay? Again, we got to distribute all of this stuff. So we've got to take 3x times x squared. So that would be 3x to the 3rd. We've got to take 3x times negative 3x, which would be negative 9x to the 2nd. And we've got to take 3x times negative 7, which is negative 21x. We've got to do the same thing for the 2. We've got to multiply the 2 times x squared. That's 2x squared. We've got to multiply the 2 times the negative 3x, which is negative 6x. And we've got to take the 2 times the negative 7, which is a negative 14. So again, if you've got 2 terms times 3, you have to distribute both of these to everything. Then look to see if there's anything we can put together. For example, okay, we've got a 3x cubed. None of the rest of these have an x to the 3rd power. So he doesn't combine with anybody. But my negative 9x to the second and my positive 2x to the second, we can add these two guys together. So negative 9 plus 2 ends up being a negative 7x to the second. This negative 21x and this negative 6x, we can combine those two guys. So negative 21x plus negative 6x is a negative 27x. And then we obviously don't have anything left to combine with our minus 14, so he just gets to hang out. And then this is the final simplified version of that. So adding, you can only combine like terms. Multiplying, you can multiply anything. Neither one is super difficult, but they look really similar. The only difference is there'll be a plus there. Oops, I wanted to put a plus. Squared minus 3x minus 7, okay? If I told you to add those two things together, you can only combine your like terms. So if we were just adding, okay, then I would just start by combining my like terms. Positive 3x and negative 3x is gone. Positive 2 and negative 7 is a negative 5. Much easier, okay? But if you're multiplying, you got to do all that distribution. So the 3x goes to everything, the 2 goes to everything, and then you look to see if there's anything you can combine. So just don't confuse multiplication with addition. That happens all the time because when you start writing these problems, especially if they mix them up, okay, on my math lab, it's nice. The adding chapter is all together. The multiplying chapter is all together, okay? But when they start mixing them together, it gets really confusing. So make sure you're paying attention to the sign that you've got going on. And again, the homework is just a bunch of practice problems of doing the same thing. It starts out pretty simple, but then it gets pretty ugly. Oh, shoot. I just saw one example that I want to talk about. There's one more example I want to show you. I'm sorry. If they do something like this, they give you some quantity to some power, okay? Most people just want to distribute the exponent, okay? It doesn't quite work like that. If you're multiplying, you can do it, but with addition, you can't. So x plus 2 quantity squared means x plus 2 times itself. So whenever you square something, you're multiplying it by itself. So when we do that, we've got to do that distribution. So we've got to take x times x, which is x squared, and we've got to take x times 2, which is 2x. Then we've got to take this 2 times x, which is 2x, and then we've got to take this 2 times 2, which is 4. Then if we combine those two pieces, we get x squared plus 4x plus 4, and that's the actual answer. So if they have you square some quantity, remember you're multiplying it by itself. Don't just distribute the exponent. Okay, the last thing that I want to cover / talk about, section 5.5, is basically the opposite of 5.4. Okay, so instead of multiplying, we're going to be factoring. Okay, factoring is kind of like, this is a terrible way to say this is bad math, bad grammar, whatever, but it's like undistribution. Okay, when you factor a greatest common factor, you are basically unmultiplying. So if I told you to take 3 times x plus 2, you would distribute. Okay, 3 times x is 3x, 3 times 2 is 6. Okay, 5.5 is undoing that. So if I started with the 3x plus 6, and I told you to factor this, okay, what we're going to do is we're going to divide out a greatest common factor. So a greatest common factor is the biggest number or variable that you can divide out of both of these terms. So if we look at the 3x and if we look at the 6, those are both divisible by 3. So 3 is what we call the greatest common factor. So if we divide him out, 3x divided by 3 is 1x, and 6 divided by 3 is 2. So like I said, if we started with 3x plus 2 and I told you to multiply, you would get 3x plus 6. If we start with 3x plus 6 and I tell you to factor, you should end up with 3 times x plus 2. So again, factoring is basically undoing what we just did in 5-4. So you're looking for the biggest number and or variable that you can divide out of everything. Okay, so if I gave you something like okay, we are looking for, if they told us to factor this, okay, we are looking for the biggest possible number and variable that we can divide out of each of these terms. So I'm looking at 12, and I'm looking at 6, and I'm looking at 3. What is the biggest number that I can divide evenly out of all of those?
3.
3, okay? Because I can divide a 6 out of 12 and I can divide a 6 out of 6, but I can't evenly divide a 6 out of 3. 3 divided by 6 is a half. I'm looking for whole numbers, okay? But 3 times 4 is 12, 3 times 2 is 6, 3 times 1 is 3. So 3 is the biggest number that I can evenly divide out of all of them, okay? Then as far as the variables go, the rule kind of is they all have to have that variable. And then you can factor out the smallest exponent. So same thing. This is a 6x to the first. That's a 3x to the first. I can take an x to the first out of an x to the second, but I can't take an x to the second out of x to the first. So again, they all have to have the variable. And then we can factor out the one with the smallest exponent. So 3x is my greatest common factor. It's the biggest thing that I can divide out of everything. Then what goes in the parentheses are basically what's left over is what I get if I divide this out of this, okay? So 12 divided by 3 is 4. And remember, division of exponents, we subtract, right? So they both have x's, I can subtract. So x squared divided by x to the first is an x to the first. Y doesn't have anything to subtract out of it, so it's just y. Okay, 6 divided by 3 is 2. If we're dividing, we subtract our exponents. 1 minus 1 is 0. We don't need to write x to the 0. Okay, y squared doesn't have anything to come off of, so it stays there. -3 divided by 3 is -1. Again, subtract your exponents. 1 minus 1 is 0. We don't need to write x to the 0 power. So this is the factored form. Okay, one way to kind of check yourself is if I multiply that 3x in, I should end up with what I started with. So 3x times 4xy would be 12x squared y. Okay, same thing. 3x times 2y squared would be 6xy squared. Okay, same thing. 3x times -1 is -3x. Okay, same thing. So this is the factored form. All right, so we've got 40, a to the second, b to the third, minus 20, a to the third, b to the fourth, plus 60, a, b to the fifth. Okay, this is an ugly problem. So we've got some kind of big numbers and we've got some wackadoodle exponents. Okay, again, remember, we're looking for the biggest possible number we can divide out. Now, I'm purposely not going to grab the biggest one. I'm going to make a mistake. So pay attention. This is not 100% how you would do this, but just in case. So let's say I'm looking at 40 and 20 and 60, and I'm like, well, wait a minute. Okay, those are all divisible by 10. Okay, so if I divide that 10 out, then I'm left with 4 a squared b cubed minus 2 a cubed b to the fourth plus 6 a b to the fifth. Okay, I can know that I did this wrong because if you look, okay, I still have a 4 and I still have a 2 and I still have a 6. What are 4 and 2 and 6 all still divisible by? They're still divisible by 2. Okay, so basically what that means is I can still factor a 2 out of there. So I didn't completely factor this. I didn't find the greatest common factor. I found a factor. Okay, but we're looking for the greatest common factor. So what that means is if I could still factor a 2 out, well, 10 times 2 is 20. That means 40 and 20 and 60 are all divisible by 20. So that's the biggest number that comes out. So if you pull a factor out and you look at your numbers you have left, you're like, wait a minute, I can still divide something out of those. I'm not done yet. Also, if you look, wait a minute, these all have A's. Shoot, I didn't factor an A out either. So I should anyway. So you can look at what you have left over and see if that's still factorable. If it is, then you didn't pull out your greatest common factor. Okay, anyway, back to the problem. We're going to do it right now. So 20 is the greatest common factor of the numbers. Okay, these all have A's. So remember, I can factor out the one with the smallest exponent, so I can take out an a to the first. Okay, these all have b's. I can factor out the smallest exponent. I can actually factor out a b to the third. So 20, a to the first, b to the third is my greatest common factor. And again, to see what's left over, I'm just going to divide. Okay, 40 divided by 20 is 2. When you divide variables and exponents, you subtract. So a to the second divided by a to the first, subtract 2 minus 1. We get an a to the first. B to the third divided by b to the third, subtract your exponents. 3 minus 3 is 0. We don't need to write b to the 0. It's just a 1. Okay, negative 20 divided by 20 is 1. Subtract your exponents. Subtract your exponents. 60 divided by 20 is 3. Subtract your exponents. A is gone. B to the fifth divided by b to the third. Subtract your exponents. That'd be a b to the second. So this is the completely factored form. So one check to make sure you have your greatest common factor out is to look when it's all said and done. So 2 and 1 and 3, okay, I can't factor anything out of 1, so it's definitely done. Also, okay, that one's got an A, but no B's. That's got a B and no A's. Okay, there's no other greatest common factors. I did good. I got the biggest common factor. This is the best completely factored form.
I know we have why. So can you explain why the 10 factor wouldn't work again? I know it can still be divisible, but if you times it by everything, doesn't it still equal the same answer?
It does, okay. And 10 does work just fine. I did factor this correctly, but remember we were looking for the biggest factor. So the fact that I can take 20 out instead of just 10. So yes, I could divide 1 out of anything and I could just write 1 in front of this and it's factored. But it's not completely factored. You're always looking for that biggest one. The GCF is the greatest common factor. Does that make sense? So
yeah.
if 20 is bigger than 10, this is the biggest number that I can divide out. So this one's not wrong, it's just not completely done. So you would get some points for something like this, but to get the full points, you got to be able to take out the biggest factor. So like I said, the 10's not wrong, it's just not done. Okay. Now, another thing. Okay, I'm going to make this kind of obvious, and I'm going to take this up a step. Okay. If you can factor out a single number, like 40 is divisible by 20, you can factor out a common quantity as well. So if I said 3x times a and 2 times a, okay, what should be my greatest common factor? What do they both have in common? Okay, the a. So if I divide that a out, then I'm left with 3x plus 2. That wouldn't change if I said that a was an a plus 1. The only thing it would change is that a plus 1 then becomes my greatest common factor, and that's what I can factor out. That's a plus 1. I tried to tuck it in there. Okay. So you can factor a quantity out just like you can factor out a number. So what that would look like is, say we have 2x times x plus 4 plus 3 times x plus 4. Now remember, I'm telling you to factor. Usually we're trying to combine and put stuff together. When I tell you to factor, we're trying to break stuff apart. Remember, we want to undistribute. We're breaking it apart. So I'm looking for something I can divide out. I can divide x plus 4 out of both of my terms. So x plus 4 is my greatest common factor. It's a factor of this because I'm multiplying here. It's a factor of this because I'm multiplying here. So again, if I divide x plus 4 out, that leaves me with 2x. If I divide x plus 4 out, that leaves me with a 3. So again, this is the completely factored form. So just like we can factor out a number or a variable, you can factor out a quantity. Which is the last thing I want to talk about today, and that's going to be factoring by grouping. Oops. Sorry, that should be an A. Okay, so let's say I have 3x plus 6 plus 4ax plus 8a. That's an A. Okay, if we look at this problem, the only factor I see is 1. So if I'm looking at like 3 and 6 and 4 and 8, the only number I can divide out of all of them is 1. So specifically, if you're looking at 3 and 4, obviously 3 is 1 times 3, 4 is 1 times 4, 2 times 2. The only factors they have in common is 1. Okay. Also, if I'm looking at the variables, this one has an x, this one doesn't. This one has an ax, no a's. Okay. I don't have a greatest common factor other than 1, and factoring 1 out doesn't help us. So it looks like we can't factor this. But we can actually factor this by grouping. And the way this works, so when you have 4 terms, one thing we can try is to factor by grouping. So I'm just going to look at this first group. So if I ignore this part, if I just look at the 3x plus 6, okay, those are both divisible by 3. If I divide 3 out, I'm left with x. If I divide 3 out, I'm left with 2. So I can rewrite 3x plus 6 as 3 times x plus 2. Okay. If I look at this group, I can factor out a 4a. If I divide 4a out, it leaves me with an x. If I divide 4a out of 8a, then I'm left with 2. And if you look now, I do have a greatest common factor. So just like here where I can factor out a quantity, when I rewrite these, okay, so if I factor this group, I get 3 times x plus 2. If I factor this group, I get 4a times x plus 2. So now I can see I do have a greatest common factor. Well, I couldn't see it to start with. Now it becomes pretty obvious. My greatest common factor is x plus 2. And if I divide him out, then I'm left with 3 plus 4a. So this is the factored form of this. So this is a strategy we can use. So factoring by grouping is a strategy we can use if you don't see a greatest common factor. Also, there has to be at least 4 terms. You've got to be able to break it up into your groups. I'm going to do one more example of that, and that'll basically finish up what we've got tonight. And then we covered 5.3, 5.4, and 5.5. So we'll do one more example of factoring by grouping. Try to make this up in my head as I go. It's not a great strategy as a math teacher, but we'll see. This should still work, okay? So we should be able to factor this by grouping. If it doesn't work, I'll make up a better problem. But anyway, so 2x squared y plus 4x plus 8y plus 16. I'm going to need x squared. I think this will work out. Okay. Now, this one actually does have a greatest common factor. So you always want to look for a greatest common factor first. If we look, there's a 2, there's a 4, and there's an 8, and there's a 16. Okay, these big numbers are all divisible by the same thing. We can factor out a 2. So if we can do that right off the bat, so we divide that out, and I'm left with x squared y plus 2x squared plus 4y plus 8. Okay, now I have 4 terms here. I'm going to try and factor this by grouping. If I look at just my first group, so if I ignore everything else, if I just look at that x squared y and that 2x squared, I can factor out an x squared, which if I divide that x squared out, I'm left with y plus 2. If I look at my second group, I can factor out a 4, which if I divide 4 out, that again leaves me with y plus 2. And then I can see, oh, look, I had another greatest common factor. So first off, I had the greatest common factor of 2. Then now, with what I had left over, I have a greatest common factor of y plus 2. So if I divide him out, I'm left with x squared plus 4. So this is the final completely factored form. It says completely factored if you can't read my crappy handwriting. Okay, so look for a greatest common factor first. If you can pull it out, it's still part of the problem. There's your greatest common factor. When you have 4 terms, we try to factor by grouping. And as long as your parentheses are the same, then we can divide that out. That's also a greatest common factor. Okay. If your parentheses end up being different, then you can't. Okay. All right. That basically finishes up 5.5. So we covered 5.3, 5.4, and 5.5. Next Thursday, we'll finish this chapter. We'll cover 5.6, 7, and 8. And then we will test the following week. So if you have any questions for me, I mean, I'm going to stick around. We've got like 3 minutes left in class. So if you have questions, I will definitely stick around and answer them. But if you're good to go, if your brain is fried, you've had enough of listening to me, you can check out. So thanks, guys. See you next week.
You know what I was kidding? You have a good one, man.
See ya.
Yeah, we did. Later.